it is 3, it is 2, it is suppose 10, it is 12, it is 13, and the corresponding values are here. Suppose it is 20, and it is some 25, it is 26, like this. This is a output. It is a target value. We call it as target. And these are the input values. That means it is a feature vector also. This is a synonym, feature vector. So I had to build one model because there is the two features here in your data set. A simple linear regression is suppose y is equal to take it as some beta naught plus beta 1 x1 plus beta 2 x2. So these are called parameters. So what is the parameter space here? The parameter space here is beta naught, beta 1, beta 2 vector is a parameter space. What our goal in the entire machine learning or AI, whatever it may be. So our entire goal is to get these beta naught, beta 1, beta 2 as a optimized values. When you give these optimized values into this function and give any input here, that input must equal to this output value. Assume that. So after training of your model, y is equal to beta naught, beta 1, beta 2, x2, when you feed this one, assume that it is a test data, 2, 10. When you give this here, 2 and 10, always here it is a direct value, or into this, always the bias input is 1 always. So when you give this, it has predicted that as suppose 22. So this is the predicted output. This is a original output. Okay, original output. Okay. So the difference between this predicted and original output is this is equal to value 2. We call this one as error. Error for this input. So if you can generalize this one, what is this error? The error you cannot take only for one record. You take for the entire thing. That is a sigma of something. So whatever, for simplicity, this error is the target value minus target value is means original output, and this predicted output from the model which you trained on the data set. Assume that this is a predicted output. I am denoting with this I. This is also I. That means for ith input in the test data, this is the error. So whatever it may be here, this target value is not changed. This is a fixed because it is it's come from the original data set, and only the change you will see here is OI. So what is OI? It is Ti minus Y is nothing but this function. So this is equal to this beta naught plus beta 1 x1 plus beta 2 x2. So it is beta naught plus beta 2 x2. So I told you that this value is fixed because it is the original output for any input, and this x1 is a value, it is fixed, and this x2 is a value, it is also fixed here and here. Now what are the changeable things in this equation for the next iteration to get equivalent? That means this must be equal to 0. So the changeable thing is beta naught, beta 1 and beta 2. So in the next iteration, you have to update these weights with some formula. There are different optimizers are there. Those optimizers generally use different techniques to update these weights. A simple technique here is uh, suppose beta I is updated with the beta I minus of eta into this change in this one. What is that change? We call it as delta. Delta of beta I into, sometimes we use this as error, and the new value is called the updated beta I. So I takes the values 0, 1, 2, whatever. How many parameters you use, those number of updations you require. So in DL, all of you listen, the total number of parameters in ML that may be limited to hundreds or thousands. But in image related CNNs, those are in millions in big cases. And when you talk about the NLP related models like a BET models or ChatGPT 4.5, these models use almost the hundreds of billions parameters they use in training phase. So those billions of parameters need to update at each iteration. Okay, for that purpose, what we require? So the updation is nothing but the derivation, the derivative of something. So that's why while to calculate this one, this value, what we use some activation functions before in this networks. So here there will be activation function. These are the transformers. Whatever the value it gets as a linear sum, and that value will be transferred through some activation function, and this value is called the activation value. So the activation function may be sigmoid, maybe ReLU function, maybe this one. So but here the output is called the predicted output, right? Predicted output. So that predicted output we use here. Okay, we use here. So that predicted output debited from this original output uh, quietly depends on what type of activation function you are using. If you see this sigmoid function, you always get this value is in between 0 to 1. It is a small value. To adjust these parameters, it takes a longer time. So that's why you require some bigger values here to update these beta naught, beta 1, all these. So based on this formula, that means if the error is very big, it takes a longer time. That's why you can take another type of activation functions here as linear ReLUs and ReLUs, all those functions. So for this, in this updation, what is this delta? The delta is nothing but derivation of your activation function involved in this, right? So for that, one by one, we'll see what is the derivation of this. This derivation here is, so this is the derivation. All of you know this. Assume that this is a x 1 by x. D by dx of 1 by x is nothing but minus a simple formula. D by dx of 1 by x is nothing but it is minus x by x square. So in a similar way, minus d by dx of dy dx of this. Whatever denominator is there, you check the minus of its derivation divided by its whole square. So minus of its derivation, what happens here? This 1 plus e power of minus x by this one. So minus this value 1 by 1 plus. So it is like a d by dx of x by y formula. So this is y by x square minus dy of dy by dx or dy by dx of this y minus this value by this one whole square. So whatever it may be, this derivation takes this value minus of this one. So when you make it a simplify, you will get this type of equation. This is nothing but this by this is nothing but 1 by 1 time you'll get it. So it is equivalent to 1 by 1 plus e power of minus x. Okay, it is like a sigma. Whatever you see here, it is a sigma minus this 1 by 1 plus e power of minus x whole square. Okay, this is nothing but sigma square. Okay, so that's why you can make it as sigma x minus sigma x square. If you take both here as sigma of 1 minus sigma. What is this sigma value? This sigma is a sigmoid value, sigmoid function. When you substitute something, you'll get some value. Once you get, suppose it is a 6 value. So its derivation becomes 6 into 1 minus 6. So it is a negative part, minus of 35. So like this. So like this, you have to calculate this differentiation. And why this differentiation is required? This differentiation, that means a change in this acquisition function, is used in updation of the parameters. So our entire goal is to get the optimized parameters, so that those parameters gives you a good output value, predicted output value, which is equivalent to the target value, original output value. So that's why you require this. But when you use this sigmoid function, this derivation gives you in this way. This is the original function, as you can see as a sigmoid function, and its derivation gives you a bell-shaped curve. That means it is always in between these two, this one, minus 6 to 6, and its maximum range is between 0 to 1, but always it takes around this 0.2. So that's why while updating your parameters, it takes a longer time to stabilize those parameters to stabilize, right? Similarly, okay, it is not fit for updating the parameters fast. So that's why you take another type of function. First one is take this ReLU function. Okay, the ReLU function is nothing but max of 0 comma x based on this x. What is that max of this one? Suppose if I take x value is equal to some 50. So this is max of 0 comma 50. This is equal to 50. If I take x is equal to minus 50, what happens? The max of 0 comma minus 50, this maximum value is equal to 0. Suppose if you take x is equal to minus 25, what happens? Max max of 0 comma minus 25, this gives the maximum value. Comparing with these two, it is 0. That means for positive, that is a same value, positive same value, and for a negative, this gives you 0 value. So that's why here you can see for all the negative values, the function value is the function is on the x-axis, right? And when you have the positive values, for all the positive values, you will see, suppose it is 1, it is 1. If you take 1 as an input, you will get a 1 as an output. If you take a 3 as an input, you will get a 3 as an output. That means it is with 45 degrees, the same value we will get it. So for positive values, you will get the same value. For negative values, for negative input, you will get a 0 here. This is called a ReLU function. What's its derivative here? So that means you can write here as this ReLU of x is equal to 0 for negatives, and it is the same value x itself in positive, in positive. When you make the differentiation of these things, you can see this d by dx of ReLU function gives you 1, uh, and 1 of x is greater than or equal to 0. That means for greater than or equal to 0, it always equal to 1. For x is greater than 0, and this is 0. Derivation of 0 is 0 for negative part. So this is the negative part. So its derivative is always stable. Okay, there is no increment and decrement in this positive part for the ReLU function. So what happens here? You won't get any maximum or minimum values in this. That's why this gives us some stable updation of this one, because all updations of the parameters depends on the derivations, but here the derivation is constant. So that's why the updation process is constant. You may get somewhere at the end, and that means the steps are somewhat bigger than the previous steps. Okay, this is a derivation of the ReLU function. Now go to this derivation of a leaky ReLU function. What is a leaky ReLU function? Here we will see here. What is that meaning? So here this leaky value is x when x is greater than or equal to 0 and p of x when x is less than or equal to 0. Suppose if I take x is equal to 10, what happens? This leaky ReLU function of this x gives you 10 only. When you check x is equal to minus 10, what happens here? The leaky ReLU gives you at minus 10. So for negative values, what is this? It is rho x or px. This is rho into x. So here this value is minus 10, but this value is you have to provide as an input. That is a factor. That factor may be some 0 point something, 0.2, whatever it may be. So not exactly 0. So when you take, suppose it is 0 point, suppose 1, assume that. What happens here? 0.1 into minus 10, this becomes minus 0.1. So minus 0.1 as a output value. So this is the 0 for y and minus 0.1 may be somewhere. So this corresponding value is something minus 0.1. So like this, it won't like a ReLU function. The ReLU function is always 0 for the negative part and it is same value in the positive part. Okay, this is the negative part. But this leaky ReLU takes some factor here. That factor, when you multiply it, that it is always positive. Remember, when you multiply it, that becomes small but never goes to 0. So that's why we can see this deviation from the x-axis for the negative part here, for the negative part of input, and you will see some small values, not all zeros. Okay, so that's why this range also may be minus infinity to infinity, and its range, its domain is also minus infinity to infinity. What is the derivation of this one? So you take a differentiation of this one for the positive part. So differentiation of this one is equal to 1. Differentiation of this is equal to p, right? So that p may be like here it is also a constant. So not only one here, that depends on the factor. So that is also always constant. Okay. So its derivative is here as 1 for positive, and this is based on the p value. The p or rho for negative part. This is the derivation of this. All of you understood this? All of you, LR of x is equal to, this is x for x is greater than 0, and this is rho x for x is less than equal to 0. So when you have negative part, its derivation is d by dx of LR of x gives you d by dx of this, d by dx of this. So this becomes as 1 for positive part. This is equal to 1. This is equal to rho. Okay, all of you know this derivation. Derivation of x itself is 1. So rho. So for negative part, you have to take a small deviation. That value, whatever you took for this of problem, and it is always for positive. The derivation is always straight. Okay, it is equal to 1. What are these derivatives? The derivatives are very important in updation of your parameters. Okay, what is the derivatives of the activation functions for tan h? What is the tan h here? This is the formula for tan h. Okay, all of you get these derivations even in mid examinations. Remember that. When you take d by dx of tan h of x, you will get 2 into sigmoid of 2x. What is sigmoid of 2x? 1 by 1 plus e power of minus 2x minus 1. This is the, this is the derivation of this is the original function tan h in terms of the sigmoid function. So you can write this one as this tan h of x is always equivalent to 2 into sigma of x minus 1, sigma of 2x minus 1. and take its derivation d by dx of tan h of x gives you derivation of this one. So the derivation of this one you will see here as 1 minus x. So here this is the original tan h function. This is a tan h function. The maximum is range value is minus plus 1 and the minimum is minus 1. And what is the derivation of this one? The derivation of this one is nothing but 1 minus of x. So when you take those values, this is always as a bell-shaped curve. So this value also changes very slow, and the range of this derivation is 1, and the minimum value is 0. So based on the requirement on different applications, how you want to update your weights, whether you want to update the weights very fast or very slow, depends on these activation functions in all neural networks. Okay. These MLP regression architectures also, I'll see here. Already we discussed this one. Anyone, what is the activation function we use here in this network? Anyone? Anyone? Clearly, they mentioned that it is a ReLU because even they mentioned did not mention this one. To identify this, if this symbol is here, that is called a ReLU activation function we use. This ReLU activation function, suppose my value is equal to 10 here. Suppose my value is equal to 20 here, and assume that the weight here is uh, minus minus 0 minus 0.76. This value is minus 0.5. This value is minus 0. Suppose 8. What will be the value here? The weighted sum here, the input is 1, the input is 10, the input is 20. So 1 into this minus 0.6, 0.6 into 1 into 1 plus, what is the input here? 10. Its connection is here. Its weight is this one. So 0.5 into 10 plus, what is this? This input is 20. This 20 carry forward to this new neuron in the hidden layer by multiplying with its parameter. So what is this? It is 20 into minus 0.8. What happens here? This is here. This is minus 0.6. Okay, multiplication of this, and this is plus 5 plus this is minus 16, minus 16 totally minus 16 plus 5, it is minus 11, minus 11 minus 0.6, so minus 11.6. So what will be the output from this one? Anyone please respond. Now you have the value 11.6 as a input for this neuron in the hidden layer, but here in this neuron we are using ReLU function. So this ReLU function, whatever function you use in any hidden layers, that will transform this input to other value. What is the other value here? What do you get as an output here?
x1, x2, and 1.
Which one?
x1, x2, and 1.
No ma, ikkada I have given these values, input values, this. So this is from data set, okay? This data set, there are two attributes are there, like the x1, x2 means there are two. So first value is, it is 10, second value is 20. I have feeded this one, okay, here, and this one. So this feeds to this neuron. In input layer, this neuron sends the same value as a output because we don't use the activation function here. So the output from this is 10, The output from this is 20. So now this 10 into this feeds to this one. This 20 also feeds to this one. Similarly for all. Okay, this one also. I am giving these are the parameters or weights for this connection. This is the weight for this connection at 0.5, and this is the weight for this connection at 0.8. So 1 into 0.6. Okay, this one into this connection is 10, output is 10 into 0.5, and this 20 into minus 0.8. So what happens here? 1 into 0.6 is this, 5 into 10 it is 0.5 into 10 it is 5, it is 0.8 into 20 is it is a 16. The total value you got here is 11.6 minus 11.6. But I told you that all these neurons are using activation function. What is that activation function? I have seen this activation function, ReLU function, right? This is the ReLU function. What it says that the ReLU of any input is the same value when that input is positive. The ReLU value of the input is 0 when that input is negative, when x is. So now tell me, what is the value as an output from this neuron? Anyone? I told you that it is a ReLU function. Anyone? What is the output?
11.6.
No, no. Now I am writing here ReLU function. ReLU of x is equal to 0 when x is negative, and this is equal to x when x is positive. What is the input here? Negative value. When it is a negative value, the ReLU function gives you as an output as 0. So this becomes as 0. All of you got it? All of you.
Yes, sir.
Hmm. Now, I am giving the weights for this. Okay, for the second one, all of you tell me. This connection is suppose 0.6. Okay, and this connection is assume that 0.8. This connection here is assume that 0.2. Now tell me what is the weighted sum here? Expand it into 1. Hello, hello. Okay. Ah, అవునండి. అవునా? ఓకే. అందరికి ఉందండి? అందరికీ ఉందా? మేడం హెచ్ఓడి పర్మిషన్ తీసుకున్నారా? ఓకే. అది ఒక్కసారి నాకు పెట్టమ్మా, వాట్సాప్ పెట్టేసి. రైట్, రైట్. ఓకే. ఓకే, 0 పాయింట్ this is 0.6 into the input is 1. Okay, plus this is the first. Second one is, what is the input here, output here? It is a 10, obviously, because it is a input layer. So 10 into this connection weight is 0.8. Yes or no?
Okay.
0.8 plus this connection, this connection. I told you that it is a 0.2, weight is 0.2. So 0.2 into its input gives you as 20. What is the value? What is the value here? It is 0.6 plus
0.6
8
plus 8
plus
plus
10. 4. Yes?
4.
4. Total it
12.6.
is 12.6. Is it positive or not?
Yes, so its answer is 12.6.
Yes, good. The answer is 12.6. So like this, the activation function acts when the input weighted sum is negative, you will get 0. So the activation functions are nothing but the transformers whatever it receives as a weighted sum from the previous layer will be transferred to other value using its formula, its function. So now here the output is, here it is 0, here the output is 12.6. Similarly, I have to calculate this one based on the weights given in this, and then this value goes to this value goes to this value goes to this value goes to this, and these weights also required, and again it will make a summation of this. Okay, here we are using the softmax function. So like this, the network goes from initial layer to the output layer. From this output layer, if you use the softmax function, you will see these output values, more number of output. If you use a sigmoid function here, you will see only two output values, okay, between 0 to 1. So like this, you can get the output value as you base. If you want the probabilities, you use the sigmoid function here. If you want probabilities with a more number of labels, you take the softmax function. If you want only the value, okay, not the probabilities for labels, if it is a regression problem, don't use softmax function, don't use the sigmoid function, you just use linear function. So whatever it receives as an input, that gives you output as a numeric value. So like this, if that numerical value is as a output value, predicted output value is not equal to the target value for any input, then this is called a error. You have to uh, try to reduce this error iteration by iteration. So while reducing this error, you have to update the parameters. That is bit and not bit one. You have to update that. You have to adjust those values to make this predicted output equivalent to the original output. This is the procedure. Okay. So in the entire learning process, our goal is to update this weights. So updation of the weights depends on the derivative of the activation function. So that's why you require this derivation of differentiation of the activation functions. So if you take the sigmoid function here in these middle layers, so this process will take a longer time because the output from each neuron by taking the weighted sum, this gives you always 0.0 to 1. So when you try to update these weights, you have to use this derivation of this one. Again, it gives you so much of time. Okay, so much of iterations are required to make equivalent to the target value from the predicted value. When you take ReLU functions, the steps may be the different. Okay, it's constantly you can update it. Okay, if you take a sigmoid function, it takes always 0.1, 0 to 1. When you take the ReLU function, it is always constant, the derivation is constant, so that the updation process is fixed. Okay, every time you will get new parameters, okay, by updating its derivation. So that's why in hidden layers always we try to take a ReLU and its uh, series like this, ReLU or leaky ReLUs, because here you can see here this is constant for positive, and this is also somewhat change is there in your negatives. So that's why you use either ReLU or LeLUs in hidden layers, and at output layer you always use either sigmoid function, softmax function for classification problem, and a linear function for regression problem. Okay, so this is about the first unit. Okay, all of you follow this book. This book is, I'll show you, I'll share you this book. All of you follow this from sixth unit onwards. Okay. So how many joined here? 13. Give me your attendance. Number one, two,
Two present, sir.
three, four, five,
4 present, sir.
6, 7,
6 present, sir.
8, 9,
9%, sir.
10,